Welcome back to Joe's Computer Museum. Last time we left off with the JCM-1, we were working on the monitor ROM program. Simple little application that allows us to view memory, put things in memory, stuff like that. Now that we have that done, we have the ability to put code into the computer. Let's start having some fun with the computer. Before we get into what I've done next, let's take a look at a few different things. First thing, if you take a look at the machine here, you'll notice that superhex is gone. He's just hanging out up here. Don't really need superhex anymore since we have the machine pretty stable, so I just went ahead and disconnected that. Also, having it disconnected from the system bus makes the bus even more stable because you don't have all that impedance and things for driving those displays. I've updated the schematic pretty significantly since the last time because there were a lot of errors regarding the decoupling capacitors on all of these. I had them basically as 10 nanofarad instead of 100 nanofarads in the on the schematic. That was just an error. They are all 100 nanos. So yeah, if you're following along with me and you're building based on my schematic, please do so with a grain of salt and do a little sanity check because I'm an error-prone dude, but that's fine. But without further ado, let's dig into the major changes here. So taking a look, well, what's different? These three chips right here. Basically, I've added sound output to the JCM-1. Main reason I want sound output, I like noise. I like blinky, soundy, squeaky things. And interfacing these I thought would be a nice step up in complexity level without, drowning myself immediately. So I went ahead and did that. Hooking these up required a little bit of a change to the address decoder, which I've added a couple little chips in here to accommodate that. It's made the address decoder a little bit more complex, but it allows me to add a lot more cool stuff down the road. So good idea to put those two things in there. So let's go ahead and flip this guy over. Let's go ahead and flip this. No, let's not flip it over yet. Let's talk about the actual chips I have in here. The sound chips I decided to go with are the General Instruments, or sometimes called microchip technologies, AY38910s. Very popular sound chip that was used in the 70s and 80s, first on home computers and then on arcade game machines later on. There are several versions of this. There's the 8910, the 8912, 8913, and all that. I decided to go with the 8910 basically because they're really cheap. You can buy them for about $1 or $2 in singles off of good old Fleabay. But they may be knockoffs, they may be pulls, they may be whatever. So, if you are building something like this, make sure you get more than one, get a couple extra. They're cheap enough, it doesn't hurt to keep them around for these kinds of projects. Especially when you have something like this guy right here, where I don't know if you can tell right here on this side, but yeah, that chip kind of got cracked in transit. Glad I bought 3 of them. I needed 2, got an extra. One of them was dead in the package, so there you go. The other chip in here is a good old 65C22, also known as the 6522, the VIA chip. The generic input-output chip that's compatible with the 6502 style processors. The reason we use this is because the AY38910 sound chip does not have the same, it really doesn't have a compatible interface with the 6502. It is designed to work with the General Instruments CP1610 processor, which is a really weird chip. It has a single 8-bit like address and data bus or something like that, and it multiplexes the buses and stuff like that. So you can't just hook it right up. You need something to interpret the interface. So that's what we use the 6522 for. So let's go ahead and flip this over, take a look at the backside, and look at some of the wiring here. Again, a little bit difficult to see the wiring on this board, but effectively what we have is the 6522 here and the 2 AY38910s. We're using one of the output output buses here to drive the inputs of both of those chips. So basically we're sending the chips an address and then data immediately after it to tell it what to do. And then we're using some of the PB control lines, the second output set here, as specific control lines for each of the chips. So I can effectively, with one 6522, I can address two chips simultaneously. And then some of these other lines are just the reset line and the clock line coming off the bus for control purposes. Other things we have in here, let's talk about the little changes to the address decoder. First change right here is a 74LSO2, that is a NOR gate. Basically what that allows me to do is bring in signals from different parts of the LS138s that already exist, so I can say, if this is active, but this is not active, do this and that, the other. And then I added in an additional 74 LS138 so I could decode another, or at least part of another nibble, so that I could better determine where I was in the address space and I didn't waste so much address space. It's kind of silly. I can just, suck up whole chunks of address space if I want to, whole pages of address space for single chips, but something tells me that I'm going to regret it less later if I go ahead and spend the extra, 25 cents on this chip and then have better decoding and better cool stuff down the road. So that's all there is with the hardware. So let's go ahead and take a look at the schematic real quick on the side PC. Okie doke. So here is the schematic. The big changes that we want to look at are right down in this corner. First, here's our 6522. It's hooked up fairly standard. We've got our data lines, our address lines, reset on all of that magic that connects to the 6522, so we can talk to, or connects to the 6502, so we can talk to the 6522 and say, hey, I want this, I want it to do that, blah, 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 blah. Here's our output port A, which go directly to the data/address lines of both of these chips simultaneously. And then these are the BC1 and BDIR, which allow us to select individual chips. So when I want to talk to chip 0, I engage these two lines here and leave those floating, or high impedance really. And then high impedance? No, I set them to a specific bit value that disables the other chip, basically. And then when I want to talk to the other chip, but this one, I set that chip. And that's really all there is to it. Right now, we are driving these guys with the standard phase 2 clock coming off the 6502, which is just a 1 megahertz clock. The 8910 datasheet says you should drive it from a 1/2 NTSC color burst reference, so like 1.78-ish megahertz. Because then the table they have in their wonderful little data sheet gives you all the values you would need in order to program specific sounds at specific frequencies. But that's okay. We don't really need that. I just need any sort of clock that has enough frequency definition to give me what I want, and then I just need a quick spreadsheet like this right here. Is it going to open? There it is. This quick spreadsheet where I can pick the oscillator up here and then then pre-calculate the divisors and all of that stuff. Put in my my values, what I want for C and A and B and whatever, and it comes over on this column and tells me what I need to program the registers to be to do that frequency. So because of this cool little spreadsheet, if I ever change that, like say I give it a 2 megahertz frequency, it auto-calculates all the thingies I need here to make specific things happen. So no a big deal, super easy. Going back to the schematic, let's take a look, go ahead and take a look at the address decoder and how I've changed that around. So this chip here and this chip here existed before. Those haven't changed. Those were the two original LS138s. But I added this extra one. And what each of these is doing is decoding part of the nibbles that are indicated by the X here. So this is decoding the very highest nibble, but only the high bits of it. This is decoding that middle nibble, but the low bits of it, and this is decoding, or it's really the whole bite, but that's fine, decoding that next one down. So that allows me to better figure out what we're doing with I/O there. And to show what I'm doing with the I/O space, I've created a quick spreadsheet here that just shows how I've laid out the I/O space. You know, we already had the ACIA in there at D0 through D3. This space is generally unused, but if I added more circuitry, I could actually decode. I could decode I/O space even more refined than the way I'm doing it now. But as for now, it's just tied up the way that is there. I went ahead and left D010 open for another ACIA in case I wanted to do 2 serial ports. Don't know if I want to or not. It may just end up being empty in the final version. But D020 is right here, and that's saved for the sound via. And so that's hooked up to the system to the sound, to that sound via, which is this chip right here. Taking a look at the memory mapper and device selector. Again, the memory mapper here is simple, and it's basically the same circuit that it was before. It has its I/O select, RAM select, and ROM select lines, and that does the same thing it did. This right here is the device selector, which is actually allows us to select specific I/O devices as we've put them into the system. So this feeds off of this new chip here, plus some signals from this chip to determine where it is in that specific I/O space. So if we're in D00, this is active, D01, this is active, D02, this is active, and so on and so forth. So I can more well refine that I/O space. Well, that is really all there was to that. Pretty straightforward setup and design. But you don't care about all that. You want to hear the machine make noise. So let's see if we can make it make some noise. So we got the computer here, and let's go ahead and plug it in and turn it on with my little 5-volt supply. And now on the screen here, we can see we have input. Yep, and it's running. So I'm going to send it a little program. It's just a little compiled application that I made in assembly language, compiled out to bytecode, and my terminal application here allows me to send files out the serial port. So that means effectively I already have a loading paradigm I can use. This app just allows me to send files to it. So I can click send file. I already got it set up. It's going to shoot the file over to the machine. And this file starts at 300. So, without any further delay, let's hear what this what sound this thing can make. Pretty cool. And since this just runs in an infinite loop, basically, I have to hit the reset button to stop it. I haven't written up a complex sound engine or anything like that. This is just a quick one-off program to show that the machine can make noise. Now, I'm going to see, let's load up another program real quick that I created. If I can find it here. Okay, this program's loading up. And what this program does is it tests the sound chips individually, or the sound channels on each chip individually. I wrote this up originally basically so I knew that I had the correct concepts, the wiring, everything put in place, and also because you know, I received this one busted chip here, I wanted to ensure that the chips that I got worked. So pretty straightforward. It just makes tones and noises on each of the channels, sends it out, so make sure that the chip works. That's really all there was to this episode today. It was pretty short, but you know, I wanted to show that progress was being made here, and we got cool things going on. What is next on the ballot? So what I'm probably going to do next is play around with some filtering on the sound chip, because right now it is just basically bare wired straight out the back and mixed directly on this breadboard and sent out this funky adaptery thing I put together to make it work. So you know, that's definitely suboptimal. So I want to put in that maybe some capacitors and a couple of resistors just to balance the sound out. That's going to require a little research. I don't know exactly how to do that, but that's what we're here to do. We're here to learn. One thing I want to add to this, and I want to get everybody's input on that, I'm thinking about splitting each of the audio channels, all three from the one chip and the three from the other chip, through some magic circuitry that is digitally accessible or digitally addressable to allow me to pan the audio per channel left and right. So instead of having it where it is right now, where one chip is the left channel and one chip is the right channel, I can basically add some extra stuff using some extra pins I have left over on this via to pan those channels whichever direction I want. It can be full left, full right, dead down the center, muted, whatever I wanted to do. So if you think I should do that, let me know in the comments below. However, I may implement it, then decide to de-implement it later, only because the chips that are required to do that are somewhere around $3 a piece, and that's kind of expensive for kind of a little bit of a niche edition. Not exactly sure what I want to do there, but let me know if you think I should put it in there. I'm also investigating replacing the inverter here on the reset line. Right now I'm using this 74LS chip here, the LS04, as effectively an inverter, because this puts out a high line. The 555 puts out high, but reset is low on these chips, so I have to invert it. However, you know, this LS chip is it's a 32-cent chip in bulk. And if I ever want to release this board, which I am seriously thinking about doing, so again, if you'd like to buy some of these boards once I'm done designing it, let me know in the comments and give me a little interest to want to build these out. Back to what I was talking about, but you know, if I ever design these boards, I want to keep the cost as low as I possibly can. Again, that's why I'm wondering whether I should put that stereo panning for the sound chips. But anyway, you know, if I were to implement this inverter with a couple of transistors and a couple of resistors, it would cost me something like 15 cents, whereas this is 32 cents. And when you're building an absolute buttload of boards, say 100 or 1,000 of them, those little pennies add up quickly. So, you know, that's what that's something that I'm thinking of doing down the road. You know, there's the concern that the reset circuit might not be fast enough, but it's not part of the switching network. It's not part of the address decoder and all that stuff. It doesn't have to be fast. It's basically, it goes low, then comes back high for about a half a second, either when you turn the machine on or when you press the reset button. So, you know, as long as it's got a nice curve, relatively flat curve, stays and then comes back up, and there's not a lot of wobble in it, it'll probably be okay. So we'll see what we do with that down the road. Future stuff, next steps. So we have gotten pretty far with this machine. It takes code, it displays stuff to the screen. We have sound. I could even do ASCII art video games with it if I really wanted to. That'd be kind of slow because of the speed limitations of the serial port, but you know, we need to come up with some better way of dealing with that. So, two major things that are really left before we can call this fairly feature complete. One is video. We want to add video to this. I really do want to add full color graphics or full color graphics to this machine. NTSC or VGA, 640-ish, 320-ish, something like that resolution. I like sprites. I'd like primitives, things like that. So the 6502 can basically just talk to a video chip and say, hey, video chip, go do this thing at that location. And then, you know, it's just like you do with the AY chips. You're not constantly polling them, telling them to make noise. You just say, go make that noise. I got better things to do. So I want to do some sort of graphics solution for that. I'm not quite sure how I want to do it. I could use some sort of AVR microcontroller. I could use a parallax propeller, which I was researching quite a bit recently. Those look really tasty because they basically have VGA and NTSC baked right in. Pretty cool. But part of me also wants to see if I can spin my own controller, my own video graphics thing, and not cheat and use a built-in controller, because, you know, part of the fun is of designing a chip or a system like this is trying to figure out how the original designers of these old machines made their magic. I don't know if I'm I don't know, what's the word I'm looking for, ambitious in that design, or if I just want to, you know, make video. Because, I mean, there's a lot of machines out there that have dedicated graphics controllers, you know. The Commodore 64 and its VIC-2 comes to mind. So, I'm not sure exactly what I want to do there. I am leaning more towards, you know, a parallax propeller or something like that, because it allows me to focus on making the machine work and getting a result. And it's a single chip. You plug it in there and it just does the thing it needs to do. Additionally, you know, if I'm going to be selling these boards, if I'm going to be handing them out to people for money dollars, it makes it easier and less expensive if I got a single chip on there. You program it with the parallax, what's the code called? The spin programming language or whatever. You throw it on there and it just works. You know, so as I build kits for people, I pre-program the chip, I send it out to you, you put it together, and it just works, and you don't have to futz around with timing and fiddling with, you know, variable resistors to get your signal to look correctly, and this and that and the other, and blah, 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 blah. So, you know. Of course, the next thing I want to do is after the video, maybe before the video. Maybe before the video might be easier to do. I don't know, save the biggest, flashiest, brightest thing for last. I'm not sure. Is add SD card support to that. There are some modules that are, again, purchasable in bulk, relatively inexpensive, that you can add to this, tie into an extra 6522 chip, and get really easy access to SD direct on the machine, and then you bang it to get data in and out so that it can have independent storage, so you're not always relying on a serial cable and a terminal and these text files and yada 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 yada. So, you know, that's a thing as well. Additionally, I want to add a keyboard. Hold on just a second. Where is it? I was playing around with some prototype shapes and stuff. I want to add some sort of keyboard functionality to the machine, so so I can, you know, design an actual keyboard of the time that's got a matrix array and a scanner and all of that stuff. Now, you know, there are ways to do that keyboard input. You can basically just have it wired up to 6522. I actually have enough input pins on the these guys here. I might be able to just bring it in via the sound chips, but I don't know. But basically, then you sit in a tight loop and you're constantly scanning the keyboard with the processor. But that doesn't make good for things like video games, for example, when you're trying to bring input off the keyboard. Oops, dropped my stick. When you're trying to bring in input off the keyboard, and you have to constantly pull the keyboard while also trying to do all this stuff, other stuff in the background. So Not sure, that I want to do it that way. I think I want to use a small microcontroller to do all of the keyboard magic and just tell the computer when there's a key has been pressed. Basically, that's the way just about every 8-bit computer of the time that was well designed, I'll put it that way, did it. The Commodore did it that way. The Apple II did it that way. They just had logic that handled that, and then let the computer, the rest of the CPU, the program know, hey, I got something for you in the buffer. Come get it. So that's not really a cheat. Heck, even the IBM did it. Every IBM keyboard had built into it effectively a full computer whose job was to scan the keyboard and then send bytes out. So, whatever. But, I'm always open to thoughts and ideas. If you guys have any thoughts of what I should add next, how I should approach it, leave comments. Let me know. I'm really open to any inputs on the design at this point. I'm starting to reach that area where I'm in confusion land. Wiring this up, for me, I'm a hardware guy, so wiring this part up was pretty easy. But now we're starting to get into things that are a little bit more complicated, I could really use some help and input. So if you got thoughts, throw them my way. Well, that's all for today's episode. Really hope you enjoyed it. While you're here, check out some of my other episodes. And remember, 8 bits are all you need.